So welcome to this, the third day of the summary meeting for the first half of the program on applicable resurgent asymptotics, which is organized by the Isaac Newton Institute for Mathematical Sciences. Remember, Isaac Newton wasn't a mathematician. He was a natural philosopher, but he was particularly good at discovering the mathematical principles of natural philosophy. And I'm pleased to say that today is really a hybrid meeting. We have people together in person in Cambridge, as well as people like me who are attending remotely. So the recurring theme of today's meeting is resurgence in quantum field theory. And our first speaker is Professor Tatsuhiro Misumi, who studied at the University of Tokyo and at Kyoto University, and he's worked with Michael Kreutz at Brookhaven on a vexatious problem of fermion doubling in lattice gauge theory. He's held positions at Keio University and at Akita University, and he's now associate professor at a university that's very dear to me in Osaka. And when I visited this university for a conference on zeta functions and topology and quantum physics in 2003, it was called the Kinki University. It had had that title for many years. But now I'm told its official name is the Kindai University. That's a portmanteau word, and they've chosen that name because it's perhaps less open to misinterpretation by foreigners. So Professor Misumi's title is Applications of Resurgence Theory to Quantum Theories, ZN Twist, Exact Wenzel-Kramers-Briand, and Phase Transition. So would you please share your slides with us?
Sure, thanks so much. Can you see it?
Fine.
Oh, okay, perfectly. Thank you very much for a very honorable introduction, and I'm really happy to be here today and have the chance to give a talk here. And I really appreciate the organizers giving me this opportunity, even though I'm one of the organizers. And today I'm discussing the application of the resurgent theory to quantum theories with special emphasis on the ZN twisted quantum field theory, exact WKD, and phase transition via localization method. And this talk is based on the more than 10 works in collaboration with these 13 people. And this is a table of the contents of this talk. Firstly, I will discuss the resurgent structure in the ZN twisted quantum mechanics and quantum field theory. And next, I'm going to discuss the exact WKV in relation to the first topic. And we will show there is a complete resurgent structure, at least in the quantum mechanics and maybe in quantum field theory. And thirdly, I will discuss the phase transition in terms of the resurgence methodology and localization technique. And the second one is has been already discussed in detail in the first focus week in the first half of this program. And the first one and the third one has not yet been discussed in detail. So I think so they will be discussion themes in the second half in autumn. So I want to make a bridge between the first half and second half in this talk. And this first topic may not be mathematician oriented, just for physicists, but the second and third ones are, I think, appealing also to mathematicians. Okay, so the first topic is a resurgence theory, or the application of the resurgence theory to ZN twisted quantum mechanics and quantum field theory. So let me begin with the introduction of the ZN twisted quantum field theory. It is a quantum field theory which is defined on the compactified space-time with a special twisted boundary condition, which is called ZM twisted boundary condition. And there are several versions of this kind of twisted boundary condition, including the fifth type twisted boundary condition, or the ZM twist for fermion or bosons. But I will call it just the ZM twisted boundary condition in all. And one of the greatest properties of this ZM twisted quantum field theory on the compactified space-time is adiabatic continuity. It states the vacuum structure, or the confining vacuum structure, and ZM symmetry, which is very important for the confining, persists during the compactification as long as we impose the twisted boundary condition. So the reasons are as follows. In terms of the path integral, so there are the Euclidean exact solutions called fractional instantons, which cause the quantum tunneling transition among n-classical vacua, and it leads to the stability of the vacuum structure. And in terms of the Hilbert space, there is the cancellation among the excited states without affecting ground states. And as a result of these two reasons, the GM symmetry, which are very important for the confining, gets stable, and it leads to the stability of the confining vacuum structure. And the point is that this theory has the non-perturbative effect and is in weak coupling region. So it is a very good place where we can apply resurgence theory. So it is a resurgence applicable, resurgence feasible theory. And because this ZM twisted QFT has adiabatic continuity during the compactification, so once we find the resurgent structure in the theory, in this kind of the ZM twisted compactified theory, we can understand part of the physics of the uncompactified original theory. This is the reason why we want to study ZM twisted QFT in terms of the resurgent theory. So let me start with one of the models where the ZM twist works very well, which is CP_1 sigma model on R cross S1 with ZM twist. This is a sigma model whose target space is complex projective space. And the simplest case is the CP1 model, whose target space is CP1. It is diffeomorphic to S2. So it is roughly the two-dimensional theory, quantum field theory, whose target space is two sphere. And the Lagrangian of this theory is given by use of this coordinate called inhomogeneous coordinate with this Fubini study metric. And in some cases, I put the fermion term too. And it is well known this theory is asymptotically free, so that it is a very good toy model of QCD or YAML theory. And we here consider R cross S1 background space-time. Then we impose the two twisted boundary condition. So this boundary condition is very simple. So for this inhomogeneous coordinate, so this is a twisted angle M, and if we take M equal pi over L, L is compactification circumference, then it becomes Z2 twisted boundary condition. And it comes to have the exact Z2 symmetry. And one of the greatest properties of this theory or this boundary condition is that it has an exact solution called fractional instantons, which map the R cross S1 space-time to half of the target space. In the case of CP_n-1 model, so it maps space-time to the 1 over n target space. And so the topological charge of this solution becomes fractionalized like 1 over 2 or 1 over n. And one of the good ways to look into the vacuum structure or the vacuum stability of this twisted theory is a two-fifth anomaly matching. So we here focus on the topological term or the theta term, theta parameter equal pi case. And in this case, on R2, just a two-dimensional CPN -1 model, so there is a mixed tooth anomaly between flavor symmetry and the time reversal symmetry. And the tooth anomaly matching states, so in this case, in such a case, either of the symmetry should be broken. But usually the flavor symmetry is not broken spontaneously. So this result indicates that spontaneous time reversal breaking at theta equal pi on R2. So it is a very good fact, a good result. But on R plus S1, if you compactify one direction, so with periodic boundary condition, without ZN twist, this tooth anomaly perfectly disappears. So this is the big problem. But here, this is the point we have to impose ZN twisted boundary condition in S1 compactified direction by this kind of the diagonal matrix. Then this theory comes to have the special symmetry, which we call ZN shift symmetry, ZNS symmetry. It is an intertwined symmetry flavor rotation and ZN center transformation. Then there appears the mixed tooth anomaly again even on R plus S1 between the flavor, this shift flavor symmetry and time reversal symmetry. So it again indicates the spontaneous time reversal breaking at theta equal pi even on R plus S1. So it seems the vacuum structure persists by imposing ZN twisted boundary condition. And this stability of the vacuum or the ZN symmetry is clearly seen in the lattice simulations of the lattice Polyakov loop, expectation value of the Polyakov loop, which is the order parameter of the ZN symmetry. This is a lattice simulation, lattice Monte Carlo simulation result. And the left one is a distribution plots of this Polyakov loop configuration by configuration on the complex plane of this P. And this is n equal 5 case. And right one is the expectation value of the Polyakov loop's dependence on the parameter beta. If this parameter beta is increased, then the compactification circumference is getting small. So this is the red points indicates the expectation value of the Polyakov loop. And if you look at these red points, even in the small compactification radius region, so it is consistent to 0. And this blue point is another different quantity, but so I note this quantity behavior is quite similar to that of the case of the periodic boundary condition. So you can find, so due to the ZN twisted boundary condition, the ZN symmetric vacuum or the ZN symmetry gets stable like this. And as I said, the expectation value of the Polyakov loop is consistent to 0, even for small compactification radius. And this peculiar behavior indicates ZN stability. And now the question is, who are responsible for this stable ZN symmetric vacuum? So it is the fractional instanton or the baryon. Here we pick up 2 of the configurations and look into the X uncompactified direction dependence of the argument of the Polyakov loop. And this is n equal 3 case. This is why it has a triangle form. And if you pick up one of them and look at the dependence of the uncompactified direction like this, and these 3 lines correspond to the 3 independent vacua of the CP3-1 model. And so this result indicates there are quantum tunneling transition between the sum of the vacua. And in this case, it is composed of the fractional instanton, fractional anti-instanton, plus fractional instanton, which we call baryon. And in this case, it is composed of the 3 fractional instantons, which makes a single instanton. So it reveals that the fractional instantons cause quantum tunneling transition among n classical minima. in the twisted ZN twisted CPN-1 model, and which leads to stability of ZN symmetry and adiabatic continuity. And I also introduced some other examples of the ZN continuity or adiabatic continuity in the ZN twisted quantum field theory. And this is the result of the ZN twisted SU3 over U1 square sigma model, which is called the flag sigma model. And on ARAW02, so we have the two types of the theta term, theta parameter, theta 1 and theta 2. So the phase diagram becomes, how to say, two-dimensional. And on ARAW02, there are three types, three kinds of the symmetry protected topological phase, and the charge conjugation broken line, and the Z3 permutation symmetry broken point. And this phase diagram is obtained from the strong coupling lattice study or tooth anomaly matching. On the other hand, on ARAW S1 with a very small compactified radius, almost quantum mechanics, we just use dilute instant gas approximation with the fractional instantons. Then we find, surprisingly, the phase diagram is completely the same, completely consistent with the conjectured one on ARAW02. So two-dimensional vacuum structure survives even in the compactified theory, as long as we impose ZN twisted boundary condition. And also the tooth anomaly also survives in this Z3 twisted flag sigma model on ARAW S1. This is also one of the good half proof of the stability of the ZN vacuum. And this is also a similar result in the N-flavor Schwinger model in ARAW S1. So N-flavor Schwinger model on ARAW2 is known to become Wess-Zumino-Witten type CFT, conformal field theory. And here we look into the chiral condensate. And if you compactify this background without ZN twist, just periodic boundary condition, the chiral condensate takes 0. And we have no sign or no remnant of the CFT or the Wess-Zumino-Witten model. But once we impose ZN twist or ZN twisted boundary condition on the compactified direction, the chiral condensate behaves like this. And this behavior is given by 1 over L. L is compactification radius, 1 over L to the 1 minus 1 over N. And this scaling dimension 1 minus 1 over N is nothing but SUN level 1 Wess-Zumino-Witten scaling dimension for the primary operators. So it means that this chiral condensate of the ZN twisted Schwinger model exhibits a Wess-Zumino-Witten scaling dimension. And also in this case, the tooth anomaly also survives. So the conclusion is ZN twisted theory again correctly keeps two-dimensional CFT properties or the vacuum structure, even the theory is CFT. So I believe, so I convince you of the stability of the ZN twisted, stability of the vacuum structure of the ZN symmetry in the ZN twisted quantum field theory. So now we have a good reason to study resurgent structure of the twisted QFT on the compactified spacetime. So before looking into the real field theory, we begin with the quantum mechanical version of the ZN twisted CP1 sigma model on ARAW S1. CP1 quantum mechanics is given by, its Lagrangian is given by this form. We put the fermion term 2, and there is a coupling term between the fermion and boson, and it is roughly given by this epsilon. And if you take epsilon equal 1, so this theory becomes supersymmetric theory. And if you take epsilon to 0, so this becomes bosonic, just CP1 model, CP1 quantum mechanics. And we want to focus on the ground state energy or ground state. So we consider a ground state effective bosonic theory. So by use of the fermion number projection by using this commutation relation and this condition. Then we end up with bosonic potential, which is given by this. It has two local minima, which correspond to the two local, north and south pole in the CP1 target space. And if you take epsilon equals 0, it has the instanton solution, which corresponds, which means the tunneling effect between two local minima, north and south pole. And the action is S1, S equal M over G squared. So this is a remnant of the fractional instantons of the anti-fractional instantons in the original CPn minus 1 model of R cross S1, twisted CPn minus 1 model of R cross S1. So this model or this theory has a very special two solutions called Bion solutions. First one is a real Bion solutions, which is given by this complicated form. But the point is this solution undergoes the quantum tunneling transition between the two local minima. One is a fractional instanton, the other is anti-fractional instanton. But it is this form itself is an exact solution. And the other solution is a complex version of the Bion solution. This is the solution in the complexified CP1 model. This is nothing but T star CP1. And in this case, phi and phi bar are independent, so they take different function. So this solution also undergoes the quantum tunneling transition between the two minima. But in this case, it takes the detour, the complex detour of the this space, complex detour, because it is complex solution. And the distance between the two fractional instantons is also complexified, so it has a complex relative distance. And from the viewpoint of the Lifshitz-Steinberg decomposition, so it is quite natural to consider to the complex saddle or the complex stationary points, because in some cases the Steinberg decomposition goes to the complexified direction. And in some case, we have the complex saddles, which can have the intersection, non-zero intersection number to contribute to the result. And these solutions are generalized to the multi-Bion solutions, which are mainly roughly given by the elliptic functions. And they are classified by the two integer p and q. P is the number of Bions, and q determines the concrete shape of the solution. And this is the case of the P, Q equal 3 and 1. So we have an infinite tower of the multi-Bion solutions, and the contributions from these Bion solutions or multi-Bion solutions are calculated by the quasi-modular integral, the integral called quasi-modular integral, which we call QMI. The quasi-modular space is a subspace around this kind of solution in the whole path integral configuration. And by performing the path integral only around this quasi-modular subspace, we can obtain the contributions from the Bion solutions or the multi-Bion solutions. And one of the prominent result is those result contributions from real and complex Bions are canceled out in the supersymmetric case. So because in the case of the supersymmetric theory, so there is no ground state energy. So it is a very consistent result. So now let's look into the ground state energy when the supersymmetry is slightly broken. So if we have the supersymmetry, the ground state energy is 0. So but we consider to deform the supersymmetry, so that now the theory is not supersymmetry. Then we obtain this kind of the ground state energy, and we can decompose it into the trans-series form. Then we find it is composed of two parts. One is perturbative part, the other is non-perturbative p-Bion part. And the first one, perturbative part, is comes from the perturbative series of the theory, and by taking the Borel resummation, Borel transform, And the Borel transform has a singularity on the positive real axis, so it has an imaginary ambiguity. And we can regard it as a perturbative contribution around 0 baryon background. On the other hand, we also have this non-perturbative p-baryon part. So this part is a p-baryon semi-classical contribution, which is nothing but the quasi-modular integral of the p-baryon solution. Then there is also perturbative contribution around p-baryon background. And we want to emphasize there is a beautiful cancellation between them. So first of all, imaginary ambiguity of the perturbation around 0 baryon background is cancelled by that of 1 baryon semi-classical contribution like this. And imaginary ambiguities of the perturbation around p-1 baryon is cancelled by that of the semi-classical contribution of the p-baryon, which leads to, and it repeatedly goes and goes, then it leads to the unambiguous exact result, which is given by this expression. So this is a very clear example where the resurgence works very well and the resurgence structure is brilliantly existing. Now we go on to the true field theory, two-dimensional CPN-1 sigma model on R cross S1. And here we start with the supersymmetric theory, and we deform the theory by this kind of the term by introducing the parameter delta epsilon. And in this case, this M corresponds to the twisted angle. So we impose the twisted boundary condition both on boson and fermion. Then we have the similar baryon solutions to the quantum mechanical case, the real baryon solutions and the complex baryon solutions, where the phi and phi tilde are independent because it is a complex phi solution. And the point is, it is approximately composed, these solutions are approximately composed of the two one-baryon fractional instantons, and it is homogeneous in complex phi direction. Now we want to derive the quasi-modular integral and the contribution from these baryon solution, real and complex baryon solution, to look into the resurgence structure of this theory. So now we have the bare effective action in the quasi-modular space to obtain the baryon contribution, which is given by this expression. But in this case, this is a quantum field theory, so there is a quantum fluctuation from fermion and bosons. So we have to calculate these quantum fluctuations and look into how this bare effective action of the quasi-modular space. And this kind of the quantum fluctuation is calculated by summing over Kaluza-Klein modes of the quantum fluctuation. But usually this kind of the sum is divergent. So we have to consider some regularization. We here take the Hurwitz type zeta function regularization. Then we end up with a renormalized type of the effective action. So what is interesting is that automatically and naturally, so there appears the renormalized coupling and the dynamical scale, CP1 dynamical scale, because it is asymptotically free theory, appears. So now if we calculate the contribution from the baryon or the baryon solution, so it includes dynamical scale or the renormalized coupling. And for example, we look into the vacuum energy. So vacuum energy, baryon contribution to the vacuum energy is given by this. Lambda is a scale, dynamical scale, and there is a dynamic scale square. And we also have the imaginary ambiguity. So, and so this imaginary, such kind of baryon imaginary ambiguity is recently shown to be cancelled by the perturbative Borel resummation, part of the perturbative Borel resummation by these people. So this result is a resurgence with renormalized coupling in asymptotically free theory. But this is not the end of the story. So there is another type of the perturbative Borel singularity, which is called IR renormalon. And there have been intensive studies on this subject by these people. And in my understanding so far, there seems to be renormalons or renormalon precursor. So renormalon precursor is the object which becomes renormalon in the compactification procedure, even in the ZN twisted compactified theory. But my understanding, or that we consider these renormalon-like or the renormalon imaginary ambiguities are also cancelled by the combined imaginary ambiguities from different Bayesian backgrounds. So at least in the ZN twisted compactified QFT, so all the imaginary ambiguity will be cancelled by some semi-classical object like Bayesian solutions or complex sum solutions. So, and we will report this kind of idea in the paper, which will appear soon. But the point is, it is still a question to be investigated further. So many people, I hope many people join to discuss this theory. Okay, so this is the end of the first part. Next, there is some relation to the first part, but I will move to a different subject, exact WKB and complete resurgent structure. And there is a first focus week on this resurgent exact WKB. And if you want to know the details of the exact WKB, please see the physical subject talk in the first focus week of this first half of the program. So the talk by, for example, Hatsuda-san, Professor Nitsuke, Ito-san, Seishi-san, Kamata-san. So in this session, I want to emphasize the exact WKB tells us complete resurgent structure, at least in quantum mechanical level. So let's review the flow of the this procedure. So most of the procedure to obtain the resurgent structure from exact WKB is summarized in this flow chart. First of all, exact WKB method leads to the exact quantization condition by using normalization condition on the Stokes curve. Then this exact quantization condition includes the Fredholm determinant. So we obtain the resolvent from this kind of the Fredholm determinant. It leads to the Gutzwiller formula, trace formula. It is another kind of the quantization condition. And by using inverse Laplace transform, the partition function is also obtained. So we end up with the partition function. And if you look into this partition function, there is a complete transverse structure, including both perturbative cycle and non-perturbative cycle in terms of the Stokes curve. And another subproduct is in this Gutzwiller trace formula, the Maslov index can be identified as the intersection number of the Lefschetz-Tenbu decomposition of the path integral. So let's look into the details. So let's review the details once more. Borel resummation of the WKB wave function is given by this form. And here Q is 2 times V minus E. And there are two types of the wave function, psi plus and minus, depending on the plus minus. And if we take the Borel resummation of the Borel transform of this series solution, WKB series solution, we find this Z quantity Z0 determines Borel non-summable curves on the complex X plane. So this is integration of the square root of this quantity Q. Then, for example, in double-well quantum mechanics, the Stokes curves, which is Borel non-summable curves on complex X plane, is given by this kind of thing. And this is the case for the imaginary H bar larger than 0. Then, so there is a Stokes curves. Then if you cross the Stokes curve, we have to multiply monodromy on this psi plus minus wave function. And if you change the turning point or the normalization point, we have to multiply the Volos multiplier, which is given by this expression. Then we can, how to say, connect the two wave function between the region 1 and region 2. And now let's look into the details of the double wave quantum mechanics. So this is the same Stokes curve figure. And there is 3 cycles. One is A, the other is B, the final one is C. C is 1 over A. And this is defined as a kind of the Stokes multiplier, the S-odd, the circle integral of the S-odd, and it is exponentiated. And actually, this A or C corresponds to the perturbative contribution. On the other hand, this cycle B corresponds to the non-perturbative contribution. And actually, it is proportional to exponential minus S bion divided by H bar. And if we consider normalization condition in x to minus infinity, so we have to, the coefficient of the psi minus should be 0. So it gives a quantization condition, exact quantization condition among these cycles. And it is given by this. And A plus A minus means the Borel summed A or Borel summed A, and Borel summed A for this region or this region. And so there is a slight change or the discrete change of the quantization condition, or there are big change of the Stokes curve between these two regions. And these changes correspond to the Stokes phenomena in the perturbative Borel summation or the semi-classical study, like the Bion semi-classical contribution. And this quantization condition leads to Transseries form partition function and the resurgent relation among the perturbative contribution and non-perturbative Bion contribution B. And if you look at the partition function, so in the non-perturbative contribution, there is a n-Bion contribution part. And so this kind of the resurgent structure is neatly summarized in the formula called DDP formula. So this S plus A tilde is a Borel summation of the asymptotic form of this cycle A, and it is also the case with SB tilde or S minus C tilde. And so this result clearly indicates the relation between circle A and circle B, which means the relation between perturbative part and non-perturbative part. And it is also summarized in the Borel resummation of the quantization condition or the Fredholm determinant. So it is clearly showing the complete resurgent structure. And one of the places where this kind of analysis works very well is S1 quantum mechanics. The quantum mechanics on a circle or the quantum mechanics with a periodic potential. We here consider Vx equal 1 minus cosine x, and we impose this boundary condition. And these two Stokes curves are the Stokes curves for these two regions for this potential with this boundary condition. And by considering the periodicity of the wave function, so there is a period, one period, because of this is a periodic boundary condition, and the wave function should become the same one up to this kind of the exponential minus theta factor. So we obtain this clear quantization condition, and it is nothing but the eigenvalue equation. So we obtain the quantization condition from this equation, and we end up with this result. again, there is a two kind of cycle. A cycle, it is perturbative cycle, and B cycle, it is non-perturbative contribution. And if you look at this Fredholm determinant, we already find there is a bion contribution and instanton contribution because it is square rooted. So there is a very clear symptom or the sign of the resurgence theory, resurgence structure. If you write it in concrete or in an explicit form, this equation or the quantization condition becomes this expression. And this is nothing but this is completely exact agreement. This is in completely exact agreement with the Gentrua's 2004 result. So this way of analyzing the this periodic potential works very, very well. And we can also obtain the resolvent from the Fredholm determinant. And if you look at this resolvent, there are bion and instanton contributions clearly. So this is the result of the part of the resolvent, so which can be seen as a non-perturbative contribution. There are the unit, it has a kind of a unit K. The K includes this part and the other part. And this part is composed of the bion plus quantum fluctuation by A. This is a bion contribution. And there is also quantum fluctuation. And this part is composed of the root B, which means the instanton. So this is why there is this kind of the theta term. And there is also quantum fluctuations. So now we can derive the partition function by inverse Laplace transformation, and it clearly shows the transseries and the resurgent structure. And this is non-perturbative part of the partition function. It is classified by the topological charge and number of bions. And it has a very complicated form. Now we denote cycle B and A as a curly B and A for some reasons. And the point is, so if you write it in concrete form, it is nothing but the bion contributions. And this is complete transseries form expression, including bion contributions. And by using the DDP formula, which is given by this expression, we find this resurgent structure or the cancellation structure is closed in each topological charge sector. And so we can write it as shown here. And this kind of structure is called resurgence triangle. So this result is partly proving that this kind of conjecture resurgence triangle. One of the sum product of this study is one thing we can obtain Vx equal 1 minus cosine nx case. In this case, the theory has the exact Zn symmetry. Then Fredholm determinant becomes a product of this quantity. And if the n is an even number and take theta equal pi, so this Fredholm determinant becomes the perfect square form. And this perfect square expression indicates the mixed tooth anomaly or the degeneracy of the twofold degeneracy at theta equal pi between Zn and C equal C charge conjugation in terms of the quantum field theory language. And now we are almost completing further study on the supersymmetric quantum mechanics and proof of the Darwin-Sum relation from the viewpoint of the exact WKB analysis. Okay, so it is the end of the second half. And finally, I'm going to discuss the phase transition and the resurgence methodology and the localization method. So as is well known, first order phase transition is understood as an anti-Stokes phenomenon, which means a change of dominant saddles or the stationary points. And the good point is the simple integral is a very good toy model to study phase transition. And anti-Stokes phenomena is also encoded in perturbative series, which are shown by these works. And the localization gives, the other thing is a localization technique gives us a simple integral expression for the complicated Suji QFT. And recently, second order phase transition is also discussed in localized SQED by the Russo entities. So the question is whether we can understand second and higher order phase transitions in terms of the thimble decomposition and resurgent theory. So this is our work. So let me review the localization method for supersymmetric gauge theories. So if we have the Suji theory with a scalar supercharge, so in this case, the action is Q closed. So we now deform this action by the Q exact term with a parameter T. Then we find that this deformed action is independent of T. So by dividing by performing derivative of this Z with respect to T. So now we can obtain the partition function or the other BPS quantity, physical quantity, by taking T to infinity limit. Then this partition function or the physical quantities becomes one loop exact around the locus, this kind of locus. Then the result is reduced into the just simple integral form. And this is one of the examples which is taken from our 3 years before work. And this is 3D n equal 3 U1 level K Chern-Simon matter theory with real mass, the parameter M. In this theory, there is only one residual variable, which is called Coulomb branch parameter. And the result or the partition function is expressed as an integral with respect to sigma. And if you consider the change of the varieties, variables, it is expressed as a Borel resummation form. The point is this exact result is the integral from 0 to minus I infinity. So now the exact result is given by this integral, and there should be a perturbative result given by this integral of the Borel transform. And there's also non-perturbative contribution, which are given by the residue of the fourth quadrant. And if you change the parameter n, the pole or the singularity goes into the fourth quadrant one by one, like this. So now we make the partition function decomposed into the perturbative part and the non-perturbative part. Then we find the action of the non-perturbative contribution is given by this form. And there is also cancellation of the imaginary ambiguity when there is a Stokes phenomena at the Stokes line like this. And this is a perturbative one, and this is non-perturbative ambiguity, and there is a cancellation, perfect cancellation. And the resurgent structure becomes trivial for such a case. And what is interesting is that this imaginary or the complex action corresponds to the known solution called complex Suji solution found by Honda. So this is the critical point. This is the complex solution. It's not a real solution. So it is critical point away from the original path integral contour. So that they should has some special relation. So we make conjecture there is non-perturbative effects appearing in the transrees of the partition function corresponding to this complex Suji solution, but it is not yet checked so far. So now let's look into the main part, the 3D n equal 4 U1 Suji gauge theories on S3. It contains 3 types of the parameters, Fy parameter, and the number of the flavor of the hypermultiplets and mass. And again, the variable is only one called Coulomb branch parameter sigma. And the partition function via localization is given by this. Now we take the 2/5 like limit, which is given by this form. Then action is becomes very simple, and we can find the saddles or the stationary points like this. And there is some function delta, which includes this part. So it means that there should be some critical points, lambda c equal 1 over sine hyperbolic n. And actually at this lambda c, there is a jump of the second derivative of the free energy. So there is a second order phase transition, which is proposed by the Russo and Tilts. And now we are looking into how the lifted Timble decomposition works in this theory. So for subcritical case, only a trivial saddle contributes. If you look at the thimble and the intersection number, you can find this fact. And if you go to the supercritical region, the infinite number of the saddles come to contribute to the partition function or the physical quantities. And between them, at the critical point, there is a collision of the saddles or the stationary points. So as I said, at the critical point, lambda equal lambda c, two of the pair, this makes the pair, the triangle and circle one makes pair, and they two of the pair collide and scatter with the angle pi/2. And at the critical point, one more thing I want to say is there is both Stokes and anti-Stokes phenomenon happens. And the point is it is encoded in the collision of the Borel singularities in the Padet-Borel transform 2. So it means this kind of second order phase transition can be detected from the perturbative series too. So it is a very surprising result. And we can make a generic argument on a phase transition as a lesson from this work. So if we assume the action in expression as this form, it is a large N form, then so when N saddles, N saddles collide and scatter with the angle beta pi, in the case of SQED, so this is pi/2, and this N was 2. So in this case, there should be phase transition. And the order of the phase transition is a scaling function of n+1 times beta. And in the case of the SQED, we have seen, so this N was 2, and the beta was 1/2. So 3 times 1/2, and scaling function of this quantity is 2. So it is consistent to the our result. So now this is a very clear result on the higher order, the second order phase transition in the large N type action. And large N phase transitions are now understood in terms of the lifted thimbles, and it means the phase transitions can be detected also from perturbative series, because these results are encoded in the perturbative series and perturbative Borel resummation or the singularities on the Borel plane too. So, okay, it's a good time to finish my talk. So let me summarize my talk. So firstly, so we have shown that baryon contributions with ZN twisted quantum field theory cancel the part of the perturbative imaginary ambiguities in QFT. And because the vacuum structure is being shown to be robust in this theory, this resurgent structure can be a key to understanding decompactified original QFT. And secondly, we have discussed the exact WKB analysis, and it figures out the complete trances and resurgent structure in quantum mechanical models, including the periodic potential models. And we also show the equivalence of the quantum conditions, quantization conditions, and determination of the intersection number. We don't have enough time to discuss this point, but this is also the results of our work. And thirdly, we have discussed the phase transition in SQED. And we have shown it is understood by thimble decomposition and resurgence. And we have shown the higher order or second order phase transitions are understood as collision and scattering of the stationary points and the Borel singularities. Okay, thanks very much.
Thank you very much. Please let us congratulate Tatsuhiro on this very clear talk of such wonderfully explicit results. I can just make a comment that two very impressive things. First of all, you show me the cancellation of imaginary ambiguities in the presence of renormalization.
Yeah, right.
And you've given me an extreme example of resurgence whereby I can start to see something about phase transitions from perturbation theory.
Yeah.
Right, so this talk is now open for questions, please.
Yeah, thank you.
Any questions or comments? You've got up to 3 dimensions. Any chance of 4?
Yes, there's some possibility to apply this kind of the method, for example, localization method, but usually in 4 dimensions. So if we have Suji like n equal to Suji, the resurgent structure gets trivial. So there's no cancellation or no imaginary ambiguity. So this is a difficult point. So what we want to do is a 4-dimensional non-Suji case. And one of the good way to do is we consider lattice gauge theory, and lattice gauge theory is in terms of the path integral. It is just a finite dimensional integral. It is very big integral, but finite dimensional integral. So in such a theory, we may be able to find the saddles or the thimbles or something like that. Then we may be able to find a resurgent structure. And we are now, we are now starting this kind of the project by using the twisted Eggwich-Kawai model. It is a kind of the reduction model of the lattice QCD. And now we are trying to find the saddles of the models or the thimbles from the saddles and the complex saddles or something like that.
Thank you. So if there are no questions, can we end the recording, please, and we can continue to talk informally.